Can someone confirm me? Slide what you are viewing on your screen might be primitive network title.
Yes, sir.
Yes,
Yes,
sir.
sir.
Oh, thank you then. Thank you very much. Yesterday we were interacting with the subject primitive admittance matrix and the representation of a cap matrix and A matrix for the further studies of formation of Y bus by singular transformation method. So how exactly matrix A or A cap is formed? So here I took an example. What is an electrical power system network? What it is composed of? How electrical elements are represented by a line segment by topological approach was just interacted in the earlier sessions as well. In that regard, I took one presentation from one of the best author of power system analysis for their direct presentation. I have picked the material and this is one of the slide where I am showing you a power system layout where we have 4 buses, 3 generators, a transformer and 3 elements. Once that is being noticed in the upper part of the representation or the single line diagram, what you find, then I am going to represent the particular graphical representation of that by graph. When I want to draw a graph of a network, I must check first how many terminals are there, nodes are there, or you may call it as a buses are there. So I find here 4, where 4 transacting terminals I will find. Bus number 1 with a generator, bus number 2 with a generator and extension to the rest of the buses. Bus number 3 is just a termination. Bus number 4 is having another generator. So that 4 buses and ground is not shown here. Ground is the hidden reference in this layout. 4 generators were represented to the bus 1, bus 2 and bus 4 with the ground as their reference. Therefore, physically I find on the single line diagram 1, 2, 3, 4 labeled buses and ground was hidden there. Then viewing all these things, when we start drawing a topological representation of that by a graph, I should put a dot like 1, 2, 3, 4 and a reference 0 or even 5 can be a reference for unless you state it. So 0 is the usual reference which is put as. Once I connect 0, 1, 2, 3, 4 on a plain paper and start interconnecting, how is that interconnection from reference to bus number 1? There is a generator. Generator is modeled as a admittance and a current source or a ideal voltage source series with the impedance. We have modeling, current source topology, voltage source topology. However, is that the connectivity from bus number 1 to reference shall be represented by a line segment which is connected to 0 to 1 by element number 1. Then we have similarly bus number 4 gets a connection from ground as a generator. You can see 0 to 4 there is an element connection and bus number 2 have a generator. Again bus number 2 gets connected with a reference to a line element. So we need not worry about numbers, but first we should see where there is a generator, that generator numbered bus 1, 2, 4, etc. in this representation shall have a connection from their respective references. In that perspective, from the ground O or 0, there is a connection to bus number 1 by one of the line segment. From the ground to a bus number 2, there is one line segment. From the bus 0 to 4. 3 is not having any generator, it is just a floating tree over there. Later, from bus number 1 to 2, is there any connection? Yes, there is a transformer. Transformer is represented by its equivalent representation by impedance, or if you call it as a reactance, then it is have representation. So there is a connection between bus number 1 and 2. Therefore, that connection is represented by a line segment between 1 and 2. You can see there is some number 6 is there. We will not worry about number right now. There is a connectivity from bus 1 to bus 2. Like that, from bus 2 to 4, there is a straight connection. You can find there, bus number 2 to bus number 4, there is an arc which is marked to bus number 4. And again from bus number 2 to bus number 3, there is another transmission line landing, which is marked as element number 5 over there, from 2 to 3. And similarly from bus 3 to bus 4, there is a line segment, nothing but representing a transmission section, which is represented. Then, after having connectivity notice, three generators having their bus got connected to reference by a line segment. Among these four buses, 1, 2, 3, 4, we have interconnection by transmission line or by transformer representation. That is represented by a line segment. Once we connect each bus with rest of the buses with the possible connections as per the diagram given or as per the interconnection in the original power system network. That forms graph of a electrical network. Later comes orientation. That's called as giving up directions for the particular element. What should be the direction of current flow if at all there is a flow of current like that. So these directions which are marked, you can see there. Then element 1 is marked just for the easiness. O or 0 to 1 element number 1 and 0 to 2 element number 2, 0 to 3, 0 to 4 element number 3. Like that sequentially elements are marked with numbers and arrows. So I was discussing in the earlier sessions also, unless and until it is given to you, you refer the direction like this only, you have a freedom of choosing the direction. Once you have chosen the direction, marked it on the particular segment, you have to stick on to that particular direction till you complete the work related to that representation. No matter, you might take downward or you may take upward. Accordingly, whether it is upward or downward, your account for that direction will be there in matrix A cap and A. So that will not make any problem to us. If it is mentioned in the numerical problem, you must adhere to that because unique solution, unique steps as you read step by step from all the participants of that problem is expected. When it is a general problem, when you are given a liberty of choice of your own direction, the final answer must be same, but steps may be deviating from one to one or one to the next different like that. So, however is that, in this problem, just we stick on, however the author has mentioned, for the generator, he has taken ground to respective buses, arrowed shooting, 0 to 1, there is a generator, 0 to bus 2, element number 2, there is a generator, 0 to 4, element number 3, he has marked with a generator over there. The rest buses, you can see there, he has given 1 to 2, element number 6, 2 to 3, element number 5, 3 to 4, element number 4, 2 to 4, element number 7. Like that he has given. Once it is drawn, marked, now this has become a oriented graph for you. From this, we need to take up impedance matrix. What is impedance matrix? Element node impedance matrix is a representation of impedance of any element with respective buses. All the elements, all the buses must be considered for that. Usually, the dimension of matrix A cap will be how many elements are there? In this case, 7. How many buses are there? There are 5 buses in fact. 1, 2, 3, 4 and O. We have to eliminate the reference bus. So in this case, I never pronounce you O is a reference. Usually, the first number what we begin, if it is marked as a 0, is treated as a reference. Unless it is said 4th is a reference, 0 is a reference here. So it need not be 0 all the time. It can be anything 1, 2, 3, 4, 5 and author may pronounce take 5 as reference. Then 5 must be treated as reference. In this case, we will consider as per the representation O or 0 is considered as a reference with respect to O clipped off. We get 4 physical buses, distinct principal buses. Then the matrix of A cap shall be 7 cross 4. 7 elements are there, 4 buses are there. Then I can definitely frame matrix A for that. If I account O also, it becomes A cap. At that time it becomes 7 cross 5. 7 complete or a full house matrix A cap or A bar. If it is reduced by one column or representation pertaining to a reference bus, that will be automatically termed as reduced impedance matrix, wherein information related to a reference bus is eliminated from the representation. In this regard, I would like to focus you how to form matrix A. I just take you another flip presentation. So I just take you another presentation which was prepared for the network topology, and we will go ahead. So what is the graph? What is the graph theory? How graph theory is used to solve the electrical problem? What are the terminologies which we use? What is a graph? Graphical representation of a network by line segment. What is a tree out of that? A graph is containing oriented elements and it may have closed loops, but tree is the one, graph or a subgraph containing all the elements and all the nodes, but no closed loop. This was what we discussed. And a solid line, a dotted line concept we have interacted. When a solid line is said, it is called as a twig or a branch. The dotted lines are called as links. Then a particular oriented graph can be converted to tree of a problem by eliminating few of the solid lines by dotted lines. How many lines I should put dotted is followed by a rule. Number of links L equal to all the elements present in the system. It can be E or it can be B in the system minus number of nodes or buses present plus 1. So I have shown you some representation here. The first diagram on the right corner having 4 buses. So you can see that there is one number repeated. 1, 2, 2 is repeated. It should be total 0, 1, 2, 3, 4, which is having a physical intact connection. There is no solid line representation. Then that must be a oriented graph. The one which is below that first diagram, right side, you find some of the lines are put with a dot. Whenever you find a graphical representation of electrical network with the dotted lines, few of them at least, then it must be a tree of a problem. You will find tree, and at the bottom you will find another representation of some other problem where few of the elements are put with a dotted and few of the lines are put with a solid representation. We call them as a twigs or branches. Dotted lines we call them as a links. So they are the possible trees of a network. Then at the corner right side you will find without any dotted lines, where some of the lines were eliminated. It shows a tree where dotted lines are not shown. Only solid lines are shown. Rest of the lines were put dotted like that. So I will take a simple example. You look into this electrical network. How exactly an equivalent graph of which can be drawn? Now observe on this example how many nodes are there. You can see at the head of the 20 volt source, node 1 is marked or bus 1 is marked. And beside 5 ohm and 10 ohm or 10 ohm joint, you have noticed bus number 2. And at the neck of 20 ohm and 10 ohm at the right side, you have been marked 3. And at the bottom of the problem, where number of elements were interacting, common terminal, where current source 4 ohm, 4 ampere, 20 volt source negative, 10 ohm return path, 20 ohm return connected to common element which is 4. So you will find 4 nodes basically in this problem. If you could view a nodal analysis, you are quite sure there are 4 nodes. And these 4 nodes were put with a dot. At the right side, with the solid arrow I have mentioned. An equivalent graph of this problem can be represented as. Look into that. There is a 1, 2, 3, 4 nodes are marked, and among them there is a connectivity. How is that connectivity? Just observe from the top of that. A is the element labeled. From bus number 1 to bus number 3, there is an arc mentioned in the upper half of the representation. Hope you are able to see my mouse actions over here. This is actually the A. A means connectivity between bus 1 and bus 3 is shown, which is by 30 ohm. 30 ohm in the representation from bus 1 to bus 3 is represented as a element A in the graphical manner. And B is shown here. Between bus number 1 and bus number 2, B represents 5 ohm resistor of the network. And element number C is represented as 10 ohm source. Can you see that? 10 ohm resistor. Similarly, I have another 10 ohm resistor between 2 and 4. Between 2 and 4, 10 ohm resistor is that is given as E. Now you will have 1 and 4. What do you find between 1 and 4? You find a voltage source. This voltage source is represented as its equivalent internal resistance? If so, because when we analyze topologically, no voltage source, no current source are involved initially. They are eliminated from our observation. In that perspective, you will find these sources will not be playing our role. So, between 1 and 2, you find 5 ohm. Between 2 and 3, you will find a 10 ohm by C, and you will find another representation 2 to 4 by connectivity, and between 3 and 4 an element F. This is how electrical network is represented by graphical connectivity on that. Similarly, I have another diagram with a voltage source, capacitor, inductor shown. Wherever there is a physical contact between any of the two buses by element, that element shall be represented by a segment. Then my next work is, once we are able to draw interconnection by graphical manner, orientation is necessary. Then orientation is necessary means we have to account them in the next. If it is so, let's look next slide, how it works. I have some other diagrams. We have some problem. Now here electrical problem is taken out. I don't require electrical circuit. I require a graphical representation which would give me indication that there are some elements with the arrows mentioned and some elements with a dotted representation and remaining elements with a solid representation. So here my intention was to tell you oriented graph. Graph is a graphical representation of the electrical network wherein all the elements and all the buses are present and connectivity is established, arrows were marked on that. That we call as an oriented graph. Oriented graph can be termed as a tree if few of the elements of that graph were put with dotted representation. The dotted representation is basically the necessity of elimination of closed loops. When you observe a mesh analysis on an electrical problem, we identify closed path, we write KVL equations for that. Nothing but my intention is to say closed path identification. So, when you have an oriented graph, in that graph, definitely closed loops are visible to you. You can simulate KVL equation for each of the closed loops. Then, to work with the numerical solution of that problem graphically, we require tree of that problem. To get a tree from an oriented graph, few of the elements of that graph need to be put dotted personally to break the closed path. We call them as links. Physically, elements will be there only, but their representation will go by dotted pattern. Once you put a dotted pattern, you will find it is just like an original oriented graph, but few of the elements are put dotted. When we trace the circuit, trace the graphical approach, graph, line by line and going around, you will find dotted lines were coming across your path. That is called break of your path. Whenever there is a solid line journey on which you take, it is on a continuous path of your continuity. Whenever you find a dotted line coming to your path of approach, there is a break of your approach. That is how closed paths were observed to be broken by putting dotted line. So in this slide, you will find few of the oriented graphs, and you will find trees possible for a certain problem. And in the earlier class also we discussed number of elements of a particular graph to be put as a dot was given as L. I'll show that in the next slide. Okay. You will find here graph and tree of a network. So in this again the similar problem is taken. You can see a graph of a particular electrical network in which I had 4 buses, 1, 2, 3, 4, and A, B, C, D, E, F are the elements interconnecting one to another. It means I had 4 buses and different elements in this. This is oriented by giving up arrows, directions to which. Once I give arrows to which and connecting all the elements with respect to buses, it is a graph. Then to get a tree possible from that, I have to identify how many elements of this graph I need to put dotted. Look at the equation mentioned over there. Number of links to be considered or number of links possible to term this as a tree, L equal to B, number of branches. It may be E also, number of elements. Some book refer E, some book refer B. So, number of elements minus number of nodes minus 1. Here minus 1 is written because outside the bracket there is a minus. Originally, it is L equal to B or E minus N plus 1. Now look into this. How many are there? In this total, if you count it, there are 6 elements. A, B, C, D, E, F. So there are 6 elements. 4 nodes. You just count it. 6 minus 4. It becomes 2. 2 plus 1, 3. So any of the 3 elements, if you put dotted, that oriented graph automatically termed as tree of that problem. You can see in the right side, similar representation with the 3 patterns. There are 3 patterns are mentioned. Any 3 lines you have to put dotted such that possible closed loops must be eliminated. Now you have to see there, if they have put the D to A, an example, D to B, B to A, some representation, and another diagram, outer 3 elements are put dotted. In the third diagram, a conical way which is mentioned, left and right side top edge is put dotted. You will find on the above 3 diagrams at the right side, no matter ABCD and ABCD over there are looking different. Don't look to the terminal, look to the graphical representation. There are 3 elements dotted in each of the diagram. By having viewed them, there is no closed path. If you trace along the solid lines and go back and try to come back, means how do you trace a closed loop? Start from a point and go around the network and try to come back to the same point. If you come back to the same point, it is a path traced by you continuous. So therefore, in the diagrams at the right side, 3 diagrams which are drawn conical way, any other diagram you pick and start from a point and try to come back to the point, you cannot come back because on your path you will find a dotted line. That is how closed loops are broken. And the same thing you try on the original oriented graph. You can come back. You start from 1, go to bus 2, go to bus 3, via element upper A, you can come back to 1. Or from bus 1, go to bus 2 via element B, go down to 4 via element E, and go back to 1 via element D. You can go back to the 1. So from 2, you can go to 3, come down to 4, go back to 2. Or from 2, you go to 3, go up A, 1, 2. So anything is possible in the oriented graph. It means to say, oriented graph really contain closed path possible. So those closed paths you need to break by making few of the elements dotted. That is the activity called as making tree from a given graph. Then to make a tree from a given graph, few of the elements you need to put dotted. Those many elements you need to put dotted is L equal to total number of elements in that system minus number of nodes of the system plus 1. So when I get in this particular problem, I will find 3 as my number. So you just look to the bottom representation where I have same diagram with the upper 3 element number B, element C and element A were put dotted. When I put it dotted, you will find element 1 to 4 solid, element E 2 to 4 solid, element F 3 to 4 solid. I mean there are 3 elements from the 4th bus touching outward, remaining 3 elements which were being connected to 1 to 2, 2 to 3, 3 to 1 were put dotted. Of course, there is no closed path visible because there is no solid line connecting each other or closed path traceable to you. Then that is called one of the possible tree for your requirement. Similarly, you will see only upper half of the dotted representation you cut and represent side. You can see there 1, 2, 3, B, C, A. Only those dotted representation were put there. This representation is called as co-tree. Co-tree is a subgraph of a main graph in which only the dotted representations were put into. So you can see a tree and a co-tree, if I superimpose, that's going to get back your original graph. Tree is a subgraph of a graph in which no closed loops exist, wherein few of the elements are dotted. The only dotted representation of a tree which is put aside is called as co-tree. Tree, co-tree, when I together call, it becomes original graph. So therefore, my intention is to tell you how a tree is formed from a given problem. So you need to have a graph which is oriented. From that graph, you need to have tree for your requirement. Next, how to put them into a matrix, we need to understand. For that, let us go next one. Why we wanted to put the information of incidence of elements with the buses? Because we were studying topological approach to the power system. It means to say solution of numerical problems of a power system using graph theory. Then graph theory has its own syntax, set of rules and procedures. It requires some representation that's called matrices or representations of connectivity of elements with buses. Hence, incidence matrix, loops, cut sets, etc. are their phenomenal representation. So for that, first matrix which we wanted to represent is the connectivity of elements with all the buses. Hence, incidence matrix was supposed to be understood. Hence, we took incidence matrix A, that was called as element node incidence matrix. Element node incidence matrix, which was having a dimension, all the elements, all the buses, called as all element incidence. Nothing but full house matrix, A cap or A bar. When we wanted to reduce it by one column or particular representation of a reference bus deleted, we called it as reduced incidence matrix. So to do that, let us take an example. Look into this example. It's the same example which was seen earlier. It means you have 4 buses. You have F. Up to F, you have elements. So A, B, C, D, E, F. All the elements with the proper orientation put on that. You might ask me, can I do my own way of orientation? Absolutely possible. You can change the direction if you find, and according to the changes which you put, look at the matrix, how it is going to get modified. Now let us understand this problem. So this problem is having 4 nodes, 1, 2, 3, 4, and several elements A to F. Now example of this, if you just see how it is put into. So look to the arrow mentioned. So how it can be transformed as A. You must see very carefully. It is capital A. It is capital A. Now watch the dimension of this. Which side you will find reduced number? Row wise if I count. Row number 1, 2, 3, 4. How many I have? 4 rows. Then how many columns I have? 1, 2, 3, 4, 5, 6. So by 4 and 6, what do you understand? There are 4 elements and there are 7 elements like this way. I mean 6 elements like this way. So 6 corresponds to element number here, A, B, C, D, E, F, and 1, 2, 3, 4 corresponds to buses. No matter, it is not mentioned. The author has mentioned, row wise when I go down, 1, 2, 3, 4, it is the buses. Bus 1, bus 2, bus 3, bus 4. Author has gone row wise representation as number of buses. Column wise representation, he has gone elements. The first column represents element A. Second column represents element B, C, D, E, F. Now I would like to state you, yesterday we were solving such problems on board. My representation went with respect to Stagg and L. Abiyad, the fundamental textbook of power system, wherein elements were put vertically, means row wise. Row number 1, element 1. Row number 2, element 2, 3, 4, 5, 6, like this way. And column wise, bus 1, bus 2, bus 3 were represented. No matter however you put, but you must identify which side is element, which side is bus. For that, it is easy trick is, whichever the side you find larger count, that is element. Whichever the side you count lesser the count, that is the bus side. With this, I can say 4, 1, 2, 3, 4. When I go row wise downward, 1, 2, 3, 4, it is the bus number 4 here. I am traceable. And elements, if I count 6, 1, 2, 3, 4, 5, 6. This is easier. But you may ask me if there are 4 and 4. A question may be like this. There are 4 elements, 4 buses. How do you understand? Yeah. For that to understand, I request you to go to each bus, incidence of elements if you trace with the Aij rule. Ith element incident to jth node oriented away from that +1. Oriented towards that -1. Not at all incident 0. If I use that rule, I will be able to understand which side is bus, which side is element. No matter, usually our problems will be of nature, number of buses will be lesser, number of elements will be usually larger by count. This is your hint, I can tell. Larger the count, you find that side can be treated as element. Lesser the count, it is usually buses. If still there is a conflict situation, you can use the rule of Aij to justify it. Okay? Now, so this matrix, let us say row number 1 I will catch. On the matrix right hand side, A equal to, it should be A cap, because all the buses are considered, all the elements are considered, it is full house matrix. If I take a first bus 1, I will look into this. A, where is A? A is connecting to 3 and 1. Arrow is coming towards that. So Aij says ith element incident to jth node and oriented away from that is +1, oriented towards that is -1, not at all incident is 0. In that perspective, element number A is connected to bus number 1. It is connected from bus 3 to bus 1, but the direction is towards the 1. Hence, you will find on the first row, first element is -1. It is to say A is towards the bus number 1. And how about B? B is towards bus number 2, going away from 1. So B is going away, hence it is +1. Element number C. C is not at all incident to bus number 1. C is connected to 2 and 3. C is nowhere in the picture of bus number 1. Hence, column number 3. So, row number 1 of a bus number 1, element number A is -1, B is +1, C is 0. How about D? D is coming from bus number 4 towards bus number 1. Hence, it is directed towards the bus number 1. You will find -1 in the position of 4. Row number 1, column number 4, you will find -1. After D, E, F, are they in the path of 1? Definitely no. You can see 0, 0 there. So, only 3 elements are non-zero. A is towards 1, -1. B is away from 1, +1. C is not there. D is towards the 1, -1. E and F are not incident. Hence, they are 0. Similarly, when I go to bus number 2, central to the problem, you will find, by look only we can say, at bus 2, B is inward, C is outward, E is outward. So, you will have B definitely -1, C definitely +1, and E definitely plus, because they are outgoing plus, incoming minus, not at all connected, 0. You just say second row when I go, it is pertaining to bus number 2. When I say first element is A, is there any element? 0. A is 0, not incident. How about B? B is put with a -1 because B is having a representation inward direction, -1. How about C? Third element, outgoing, +1. How about D? Not at all incident, 0. E, outgoing. Outgoing, I said Aij, ith element, jth node, incident, and moving away is plus, moving towards is minus, and not at all incident, 0. You will find E is outward, hence it is +1. F is not at all incident, hence it is 0. So, likewise, if I move to third bus, at bus number 3, you can graph, say C is inward, A is outward, F is outward. So when I say A is outward, A must be +1, B is 0, T is inward -1, D must be 0, not connected, E must be 0, not connected, and F must be outgoing +1. We can watch there. Row number 3, when I go there, the very first element is A. Bus number 3, element A, outward, +1. Element B, not connected, 0. Element C, inward movement, -1. D, not connected, 0. E, not connected, 0. And F, outward movement, definitely F. It's a +1. Similarly, when I come to bus number 4, graphically you can say at bus number 4, how many elements are interacting? Only 3 elements. One of the element is D, another is E, another is F. D, E, F are the only non-zero, rest all 0. You can do it again. When I go to row number 4, first our element is A. A is 0 because A is not at all incident, not interacting with our node number 4. Then B is not incident, C is not incident. Hence you will find 0, 0 and 0 in that position. 0, 0, 0. 3 zeros initially. And D. D is the element getting connected from 4 to 1. And D is having an outward movement, outgoing direction. And it must be +1, which is witnessed over here. And look to the next element, E. E is the element coming from bus number 2. 2 down to 4. Hence it must be incoming, it is -1. Respectively F. F is an element interconnected 3 to 4 and it is the inward movement, hence it is -1. So by this way, I can convince you and I can configure you, yes, incidence matrix of a given problem can be configured very easily using AIJ rule. Now in the downward movement, reduced incidence matrix I mentioned. When I want to make a reduced incidence matrix, what is the meaning of that? The meaning of that is one of the bus information to be deleted, reduced. So therefore, in this configuration, we had 4 buses, 1, 2, 3, 4. And observe the matrix at the lower page of the slide. 1, 2, 3. 4th bus is deleted. And once the 4th bus is deleted, just observe which is that bus mentioned there. So it is going to have number of rows in this problem, 1 lesser, number of columns as usual, A, B, C, D, E, F as usual, and one of the row pertaining to reference is deleted. Now you can trace. You can trace it, which is the row remaining there, or you can just take example just closer to you here at the left side. Another example is mentioned with the arrows. Element is A, element is B, C, D, E, F, 1, 2, 3, 4. Another example is shown to you. For that example, if I draw incidence matrix at the lower left corner, you will find 1, 2, 3, 4 and A, B, C, D, E, F, all the elements. Upper problem is limited to A only, means full house matrix. Another problem which is mentioned in the red line is having its incidence matrix at the bottom of which having 4 nodes, all the 6 sides. You can see that. You can apply a rule. You can use that as full house matrix. And you can see from that left hand side matrix 4 cross 6, 1, 2, 3, 4, A to F, getting reduced to 1, 2, 3 and A to F. You can see there, last row is deleted. Physically you can watch. The row number 4 is absolutely deleted off from that. Then it became reduced incidence matrix. Reduced incidence matrix is the matrix obtained from all incidence matrix. Element node incidence matrix from which one of the node or a bus data is deleted. In this problem, without having noticed much, we can say bus number 4 is reference, 4 bus related information is clipped off. Clipped off. That's what I wanted to convey you. So this is how a reduced incidence matrix can be framed, can be seen from this. So if you have network analysis textbooks with you, or even your free time, just Google for a network topology and incidence matrices. You could get lot of examples. And also even I have YouTube videos collected. I have in fact YouTube videos. No, they may not run, I hope. If you want, I can just show you also. So a sample video is available in the YouTube of 5 minutes or 6 minutes, explain you how exactly element to element -1, +1, 0 is put into representation. I shall request you can just view into some of the such observations. Okay, so this was my intention to just make you, and later these are not required for right now. Fundamental loop matrix, cut set matrix, other operations related to which not required. I will not go ahead. So my intention was just to make how A matrix is obtained or A cap is obtained. A is formed from that. That was my intention. So from this, I'll come back this particular problem which you will find. Okay, a electrical problem, graphical representation, orientation, whose representation into terminology should be worked out. So for this, if you could see, this problem is again represented by a network, interconnection, and again you will find here number of elements, number of buses, circled side shows buses, and numbers only shows elements. So you have full house matrix and O is deleted here. You can see here there is no 0 mentioned. Directly author has written reduce the incidence matrix only. He called it as a bus incidence matrix A. Bus incidence matrix A means reference bus is not included. Hence it is directly shown you 1, 2, 3, 4 and their incidences directly. So hope this slide is visible to you. I would like to mention where is -1, how is this, and I'll go to my power system load flow fundamentals. Hope this slide is visible to you all. May I get a feedback from you?
Yes, sir.
Yeah, please. Thank you then. So this was the problem we began, and I took you diverse how A matrix is obtained for a given network by topology, and I am coming back to this electrical single line diagram, how a graph is represented, how usually orientations are given. If orientations are given like this, how to represent the interconnection in the form of matrix, I wanted to convey you. Suppose this problem was considered as a reference to us, so many elements by number 7 I have, so many buses, physically 5, but reference is taken out, hence it becomes 4 cross 7 representation on this slide. Okay, then how to put the elements over here? Element number 1, 2, 3, 4, 5, 6, 7 you notice that, and buses 1, 2, 3, 4 you notice at bus number 1. I stand at row number 1. With respect to bus number 1, how many elements are interacting incident to the bus number 1? At bus number 1, if I see on the slide, element number 1 is towards that, element number 6 is away from that. Aij rule if I apply, I'll be having one is involved, Aij, ith element incident to jth node. It means A1, 1. Ith element, I is 1, J is 1. Aij, ith element is incident to jth node and oriented away from that is +1, oriented towards that is -1, not at all incident is 0. In that perspective, second rule applies. One is incident, but it is oriented towards the node number 1. Hence, I have -1 in the position of element number 1. Bus number 1, row number 1, I am tracing element number 1. In the first column, I have -1. And element 2 is blank, nothing but 0 for me. 0, 3 is 0, 4 is 0, 5 is 0, and directly 6th element. 6th element is nothing but A6, 1, Aij. Aij, this is incident to bus number 1, but directed outward. When it directed outward, rule number 1 stands with me. Aij is 1 if ith element is incident to jth node and oriented away from that. In that way, this is going to be a +1. And there is no 7th element incident, hence it is 0. So it is physically seen. There are 2 elements interacting at bus 1, 2 elements in the first row are non-zero. Rest are absolutely zero. Now similarly, if I go to bus number 2, at bus number 2, how many elements I find? Element 2 is inward, element 6 is inward, element 5 is outward, element 7 is outward. It's very clear. 2 of the elements which be with the minus, rest 2 will be plus. You can watch that. Element number 1 is 0, not there. Element 2 is minus 1 because it's the inward. 3 is 0, 4 is 0, 5 is outward, hence plus 1. 6 is inward, minus 1. 7 is outward, plus 1. It's with a definite rule. What the rule is prescribed, the same rule is being used, and you have to mention plus 1, minus 1, 0, however applicable to the application. So at bus 2, I will find 4 elements interacting. Similarly, if I move to bus number 3, by graphically you will find 5, element number 5 is also inward, element number 4 is also inward. It's very clear. Both the elements 4 and 5 will have minus, remaining all the elements shall be 0. You can look into bus number 3. Means when I go down by rows, third row, when I move lateral right side, first column 0, no incident. Second column 0, third column 0, fourth column is element number 4, minus 1. Fifth column is element number 5, minus 1. Sixth, 7, absolutely 0. This way, it's a very easy approach. May it be lengthier, but it's a very easy approach one would get into representation. And at bus number 4, you will find 3 of the element. Element number 3 is inward, element number 4 is outward, element number 7 is inward. So you will find it. 1 is 0, 2 is 0, I am at bus number 4, fourth row. 1 is 0, 2 is 0, 3 is minus 1, 4 is plus 1, 5 is 0, 6 is 0, and 7 is minus 1. That's the end of our A bus. Means A matrix which I would write. Directly we wrote reduced incidence matrix. The work related to 0th bus, reference bus is not at all done. So hence it is called one step advance. Otherwise, if at all if I account 0th indication, bus number 0 also, it becomes full house matrix. From that, I have to eliminate one of the representation of the reference bus, then it becomes reduced incidence. So this was what we wanted to interact. So why we came up to this point? This matrix A is of our uttermost interest. Yesterday we have seen when we apply KCL for this, KVL for this, how this will work. So in that way, A transpose into I vector equal to 0. If I apply KCL at each bus, incoming current must be equal to outgoing current. Like that we have seen. And the voltage at a branch 1, V1, V6, V2, etc. We have seen in the yesterday's representation. It is the difference of bus voltages of the circled number. Suppose I want to write V6, branch voltage of the element number 6. It is E1 minus E2, which I referred capital notation. In this book, the author has referred capital V notations for buses, small or lowercase representation for branches. So this way it is being written. So therefore, that is what we have seen. Matrix A becomes very interesting for us for our Y bus by singular transformation method. So this was the fundamental we wanted to know. I just took you back to the presentation for clearing your doubts or making it legible to you compared to the board work which you have done. Then it is nothing but how the same thing is put into. So we have voltage of branch 1 is E0 minus E1, nothing but V0 minus V1, nothing but minus V1. Bus voltage at 2 means element 2 voltage stand as 0 minus V2, it is minus V2. And similarly bus voltage 4, 0 minus V4, minus V4. And bus voltage at 3, it is same as same voltage. Because it's a differential, it's a floating point. It's a floating point, not having any reference from this. It is the same as this voltage. So it is V3 equal to minus V4. And what is V4? V4 equal to 0 minus this. Or you can come by other way. Then V5. V5 is the potential. Where is the 5? Element number 5 here. Difference between V2 and V3. Like a nodal analysis, what we refer. Any voltage between two nodes, if you find that the branch voltage, differential potential, nothing but voltage of that branch. This was seen by matrix A's approach. And how to write a KCL? That also we have seen. KCL, when we apply KCL at this junction, the current incoming must be equal to current outgoing. So author has used one new technique. Suppose there is an injection of I1 here, capital I1. Where all it will go? It will go towards 6, getting I1 from this. You can see here, capital I1 is equal to incoming current minus outgoing current plus. You can see here. So if you make it 0, minus 1 if you take other side, incoming current must be equal to outgoing current. In this way we can do it. Okay. This is how this was seen in the earlier class. Now in the next class I refer directly the particular representation this way. Derivation of Y bus, nothing but admittance bus from fundamental. That's called as Y bus by singular transformation method. Y bus by A transpose Y primitive into A.